find the standard form of the hyperbola. So it definitely needs to say hyperbola versus ellipse so that you know which type of conic you're working with, because technically both of them have two foci and vertices. So you could really write an equation for either one if it didn't tell you that it was a hyperbola that we were trying to look at. So we have vertices and foci. Do you want to graph them so that you can look at it visually? Then you have, like, you understand where everything is kind of spaced. So we have a point at -1, 2. And 5, 2. So those two values are the furthest points now for hyperbolas. They should be kind of outside. The vertices would be then at 0, 2, and 4, 2. And after you graph those, then you could say, yes, it has to be a hyperbola, even if I didn't say it was a hyperbola, because now the foci are out further. So once you have it graphed and you see the foci are further than the vertices, then we can definitely say we have a hyperbola that we're dealing with. So Marie, what can we tell just by looking at those 4 points?
You could find, since you were given the points, you could look at the center. You can find the center.
Yeah, we can find the center because it must be in the middle of each of those pair of points, and that center would be at 2, 2. So the center is in the middle at 2, 2. What else can we tell? Zach, what else?
Oh
Oh
no.
no.
You can also tell if it's horizontal.
Yeah. So, that's right, green doesn't like me all the time. There we go. This one's horizontal. All those points lie on that same horizontal transverse axis. Where all the important pieces lie. What else, Zach?
I think you can even figure out your A and C values.
Yeah, we can. We can figure out A and C. So from the center to one vertex is A. From the center to one focus is C. So that means A is 2. Oops. I don't know why I put it underneath. And C is 3. David, what else can we do?
We can find the c squared equals a squared plus b squared.
Great. So this time you're adding those two distances together. That creates the focus, each point to be further away from the center because we're adding those together. And David, that gives you, cannot write, b squared is equal to 5. So c squared is 9, a squared is 4, 9 minus 4 is 5. So that's all the information we need. We can now plug it into the equation. If it's horizontal, which variable goes first? X. So now it doesn't matter which one is bigger because actually b squared is bigger than a squared. That's okay. We're looking at the positive term, the positive variable. That goes first when it's a hyperbola. So we have x first with a always underneath the first term. So whatever's positive gets a, that first term. The y has a minus sign in front of it. That makes it a hyperbola. That gets the 5, and then it's equal to 1. Any questions with that information? So why don't you take a look at your number 27. Has x squared minus 9y squared plus 2x minus 54y minus 80 equals 0. So I just stuck the 80 on the other side. So David, Lucas, if you complete the square, what do you have for the x's when you complete the square?
You'll have. You want me to factor it too, or?
Yeah, what do you have? Yeah, that's fine.
So you'll have -1. Am I looking at the wrong problem? Yeah, I'm looking at 29.
Okay.
X plus 1 squared.
So x plus 1 squared, and then with the y's, there's a 9 in front, and we end up with?
Y plus 3 squared.
And on the other side, I believe you add a 1 and you subtract an 81 while you're completing the square. So you get 0, which was not wrong. It's correct. Can you divide by 0? No. So you can't divide by 0. But there is still something that you can do to try and work through the problem a little further. So no, this isn't standard form of a hyperbola. It can't be an ellipse. It not be a circle, and it's not a parabola. But what could you still do to try and work through the problem? Like, think algebraically. What else can we do algebraically, David?
Can you make it into like y equals?
We could try and get it into y equals. How would you try and get it into y equals, David?
Well, I was gonna say, could you move the 9 y plus 3 squared to the other side?
Yeah, let's take that to the other side, because if it's equal to 0, then you're able to move things from one side to the other. So let's just take that negative term and place it on the other side. If you have a squared term on the left and a squared term, single squared term on the right, there's no extra addition or subtraction that are being added and subtracted. Bless you. What could you do? Take the square root. Yeah. Because taking the square root, as long as you have one term equal to the other, that's an easy way to get rid of a quantity that's squared. So over here, I'm still going to keep this as like a parentheses, so we have that x plus 1. And on the other side, the square root of 9 is 3. I'm going to keep it as y plus 3. Now, if you take a square root, what goes in front of the quantities when you take a square root? A plus or minus. So we've really got a plus or minus, a plus or minus. And I'm keeping it grouped like this for just a special reason, which we'll see in a minute. David said we're supposed to get y by itself. So, David, one thing that you'd have to do to get y by itself would be,
You could either divide by 3 or distribute it.
right, so you could either divide the 3 out or distribute it. Let's divide it out so that we can get it to the other side. So if we take it to the other side, I'm still keeping this in parentheses. But on the other side now, I have plus or minus 1 divided by plus or minus 3. So you don't need 2 plus or minus, that's just redundant. So we have plus or minus 1/3 and then x plus 1. And that's as far as I'm going to take this problem. Because it still is in a form, what type of graph would this make? A line. How many lines?
2.
2. So here is our slope. This is still h and k. So my slope is 1/3. It has a center at -1, -3, but that's actually where the 2 lines intersect. I'm going to bring my comb back over to kind of show you what's happening, because it's still a conic. If you looked in the back of the book to check out the answers, it used the word degenerate conic. So it starts out looking like a conic equation, but it's equal to 0. So we can break it down a little bit, and you end up getting 2 lines that intersect. So remember, I'm supposed to have 2 cones because it's a double napped cone. So the lines, instead of slicing through the cone for a hyperbola, which if I had a cone on top, literally, like it'd be a vertical line or vertical plane slicing through. They're on the edges of the 2 cones. So going on the edge of one cone is my line with a negative slope. Going on the edge of the other would be a line with a positive slope. And they meet in the middle where the 2 cones would meet. That would be the center of the graph. So it's called a degenerate conic, because it's not truly a conic, but it still is created from the conical shape. So that's why that one's a little special. But it goes on the edge, so my 2 planes are like just slicing, just touching the edge of both cones. So we have 2 lines, they meet at the center, they connect at the center where both my cones would be connecting together. Questions on that? That only happens every once in a while. It was a good problem to throw in there. So questions?
So are we ever gonna have like a problem where it just ends in like no graph can be made from
No.
this? Or
They'll always create some type of graph. Yeah. David?
Would something like that be on the test?
Well, it could be. I mean, this is honors sugar free calc.
I don't want that answer.
So, I mean, next year in AP Calc, every problem is some type of application. Every problem you do will never be the same as the one you did in class. It's like everything is that analytical analysis outside of the box thinking. That's the tricky thing about calculus. Like you do 2 things. You integrate, you differentiate. But it's a lot of like applying that stuff outside of the box. problems assigned when I taught regulatory and pre-calc. I'm pretty sure I assigned that problem, but I didn't put it on the test. That was eons ago. So we're going to look at a couple of more problems in the notes. So if you just flip and turn to page 14, go to the bottom of page 14. So we have like the bottom of page 13 with a little question, the bottom of page 14 with a little problem to go over. This problem has us using asymptotes to help us try and come up with an equation. So just read through it and see like how much can you figure out without using the asymptotes. So save the asymptotes, that second part of the graph or question. But what can you figure out from having two vertices? How much of the problem can you create with a hyperbola? Having two vertices. David, what do we know?
You can find your center, and you can tell that it's a vertical hyperbola. And then with your asymptotes, you're going to find, could you find the b value as well?
Mm-hmm. We're going to find b with the asymptotes. So what's the center here?
So your center is going to be 3, negative 3.
It's 3, negative 3 or 3, negative
3, negative
2? Yeah. So we're at 3, negative 2. So we can get the center. You have the center, so then you can find A, because it's the distance from the center to 1 vertex. That's 3. We know that it's vertical, so we'll try and plug all of that information into the equation. If it's vertical, Marie, which term goes first? Right, so the y is first. The positive term is the direction that the graph goes. So vertical means y is the graph, or the term that moves up and down, so y has to come first. So it would be y plus 2, because k is negative 2. We know a is 3, so underneath that is a 9. A is always in front. Then we got our minus sign. X minus 3. I don't know b squared, so I'll just leave that there for a moment. And it's equal to 1 because standard form is supposed to equal 1. So by having a set of points, we can pretty much get, I'd say, like 90% of the information filled in. So David said that we can use the asymptotes to help us find b. And if you just look above, looking at that asymptote equation that we talked about yesterday, we have a vertical graph. Here's the slope of the equation that represents the asymptotes. So whatever your slope is represents a over b. Because my rise is 3, the run, which is the other distance, is b. So if we use slope, and the fact that slope is equal to rise over run. The rise is 3, so I can plug in a 3 there for my rise. But we don't know the run. However, what's the slope of the asymptotes? 2 or negative 2. It doesn't matter which one you use. So we know the slope of the asymptote is 2 or negative 2. So we can plug that in. So we're using the slope equation, rise over run, taking the slope of one of the asymptotes, and then solving for b. So b is going to be 3 halves. Because I knew a, I knew what the actual slope of the asymptote was, so I just need to find that missing part. So now we can finish our equation. Y is in front because it's vertical. A is always underneath the first denominator. X is second, since it is a vertical graph. And now if I have b is 3 halves, b squared is 9 fourths. So you don't need to know the fact that the asymptotes they give us have a y-intercept of, 2 and negative 8. That doesn't affect the slope of the graph. B is the only part we need to find. and we can use the slope of the asymptote to find the b of our equation. Questions? So the last two pieces that we're going to talk about is trying to start to summarize everything, and that talks about the eccentricity and how eccentricity can help us determine the type of conic we have. But then also just by looking at the expanded equation, we can also determine, based off of some conditions, the type of conic we have. So eccentricity, we said, yeah, it's the stretch of the graph. So with an ellipse, it was how narrow our oval was or how fat and round it was. With a hyperbola, it's going to be how skinny the branches are or how wide the branches are. Anybody remember what we used to find eccentricity? It was something over something.
C over A.
Mm-hmm. So it's C over A. So we're looking at everything that lies on that same horizontal line or the same vertical line. So the distance from the center to the focus, the distance from the center to the E vertice. If that number is greater than 1, then it's a hyperbola. Why does it have to be bigger than 1 for a hyperbola? Think about the graph of a hyperbola. Why would the eccentricity be bigger than 1, David?
Because on a hyperbola, your C is greater than your A value.
Yeah, so looking at the graph that we did yesterday, C, actually this was even the warm-up, is outside. It's further away from the center than the A is. So C is bigger than A, forcing the graph to be bigger than 1, having eccentricity bigger than 1. So they kind of go together. A little bit of information. If E is close to 1, so that means that my foci are really close to the vertex. We have narrow branches. The further out the focus is, the wider the graph becomes. So we'll just say if E is larger, then I will have wide branches. So the further away that focus pulls away from the vertex, kind of pulls the branches out further and further as well. So we talked about 4 different conics. Each conic actually has an eccentricity. I know there are only 3 listed. We're going to list a number 4 just so that we can kind of think about all the eccentricities. So if it's equal to 0, what conic do you think it would be if the eccentricity was 0?
Circle.
A circle. Why'd you say circle, David?
Because like all around the center is the same distance.
Yeah, and there isn't a focus in the middle. So I don't have that C value because technically the focus is the middle of the graph. It's the center. So there isn't really that C over A value. So when the eccentricity is 0, it's a circle. When it's between 0 and 1, that's the ellipse. And the reason it's between 0 and 1 is because the distance is shorter than A. So when I take a number smaller than A, I'm going to get a number, when I divide, that would be between 0 and 1. When it's greater than 1, it's the hyperbola. And we just said that's because the C is past the A value, it's larger than it, so the number on top of our eccentricity value will give us a number bigger than 1. So what would the other option be then? Right?
A parabola.
A parabola. What do you think the eccentricity of a parabola is? Not all real numbers. What's the option that I don't have up here? So it has equal to 0.
Less than 0?
In between 0 and 1, less than 0, can't have a negative amount. E equals 1. So what does a parabola have besides a focus? A vertex. And what else does it have? It has a focus, a vertex, and kind of like an asymptote. It begins with a D.
Directrix.
The directrix. And the distance from the vertex to the focus, the vertex to the directrix, is the same. So if the distance is 5, it's 5 over 5. If it's 6, it's 6 over 6. So the parabola has an eccentricity of 1 because the vertex is always in the middle of the focus and the directrix. So that's why that eccentricity is 1. The last thing underneath here. So that's one way to classify a conic. If you can find the C and the A, you can decide what type of conic you have. Except that means you have to do a little bit of work. Without doing any work, we can classify them just by looking at the equation. So the expanded form of a conic, it has ax squared plus cy squared. There really is a b in the middle there. It's not that I don't know my alphabet. There's a term in there that we don't use very often. Technically, there's a bxy there, and that bxy is what tilts our tonic and makes it go diagonal. So the graphs that we do don't have that in it, making the graph either be vertical or horizontal because it's parallel to either the y or the x-axis. There's a little bit of trig involved with that bxy term to get the graph to tilt. So we're skipping over it, and not having the slanted axes, but there really is a graph that you would have your axes slant so that our parabolas, our hyperbolas would tilt. So we have this huge extended form, but without doing any work and just looking at the form, so you don't have to complete the square, you don't have to find any pieces of it, by just looking at the equation you can decide the type of conic. The first one says if A is equal to C, meaning they are the same numbers. So if I have 3x squared plus 3y squared, then I have a circle. So we're focusing on the squared terms. If both my squared terms have the same number, it's a circle, because the radius then is going to stretch the same way up and down and left and right. The second one, it says if the parabola has a times c equals 0. But it says not both. If you have one squared term, either x squared or y squared, it's a parabola. So that's what makes it a parabola. It only goes one direction. It doesn't have both pieces. So it's either an x squared or a y squared. So again, we're focusing on the squared terms. The third one, an ellipse. It says they have the same signs. So it's both positive for x and y, or they're both negative for x squared and y squared. And then the last one would be the hyperbola, and it says they have unlike signs. So we have one that's a positive and the other one that's a negative. So it's an ellipse if everything is positive, or it's all negative. It's a hyperbola if you have one positive x squared term and a negative y squared term, or vice versa. So looking underneath, there are 3 examples here. No work necessary, so you don't have to do any work. Look at the squared terms. That's what you need to focus on. So in letter A, what terms are squared? Just the x. So if you just have one squared term, Zach, it would be a parabola. And that's all you need to do. One squared term is a parabola. In letter B, looking at those squared terms, not the rest of it. What would you say this graph would be if we complete the square? Because
There's a positive and a negative.
right, there's a positive and a negative. So they're both not positive or they're both not negative. You got one of each. So unlike signs. And then the last one, Aaron, what do you think about letter C?
I think it's an ellipse.
And that's because
A times c is greater than 0.
yeah, a times c is greater than 0. Both of them are positive. A positive 2x squared, a positive 4y squared. Questions? So I said your homework is a little different. If you go to the last page of your packet, the very last problems, I think it's 16, has those 4 problems that you're asked to identify the type of conic. So from your review, I'd like you to do 12 through 16, just the last 4 problems. And in those last 4, you will have an example of each conic that we worked on, just to start kind of refreshing. But the last number, 16, has the ones where you're classifying. And then the other problems I'd like you to do are from the book, and I can't remember what page we were on. Walk over here. Page 655. So part of this is already on your assignment sheet. I'd like you to do 41 and 47. Those two you'll have to do a little bit of work for. They're identical to the 2 problems we did where you're finding the standard form of the equation.
It says on the page 665.
665, thank you. I appreciate that. 665. And then you're going to look at 55 to 63 odd. And those group of problems are also just classifying. So you're classifying for 55 to 63 odd. Number 16, you're classifying the conic as well. And then there's a couple of problems, I think 5, that you're going to actually do some work for. The book are the hyperbola problems, and this is a 41 sloppy handwriting. Questions? So the last 4 problems of the review, a couple of problems in your book. Tomorrow we will continue to just work through some problems. I think I have another hyperbola problem for us to look at.